So you arrive at low Mars orbit. So you're basically duplicating what you already did at L1. You have a package with a robot and a complete set of parts for a docking truss. The robot builds the docking truss. It attaches the rails. It attaches the docking discs. And vehicles can then start attaching themselves to it. And then they would attach solar arrays and the crew clusters and anything else you need, like attitude control systems and so on. Then you're all set up in low Mars orbit. And there is the low Mars orbit way station. Here's the vehicle arriving. Here's a robot transferring cargo into a cargo ferry. And it's got 4 solar panels. And the panels can rotate. It doesn't show it properly here, but they're supposed to be able to rotate that way. And these are supposed to be able to rotate that way, so you can aim at the sun any time here on the day side of Mars. And it also has to have batteries, just like the space station for going on the dark side. It's a slightly different view of it. Oh, this one shows that this is compatible with using the Aldrin cycler as a different way for getting the crew to Mars. Using the direct boost is probably more efficient for cargo, but you could use the cycler for the crew. Either way. So right now, this is what we've just demonstrated recently with the Curiosity landing. You can land about 1 ton on Mars right now. That's the maximum we know how to land right now. There's no combination of any equipment that allow us to land even 10 tons on Mars right now. We need to land, the cargo ferry has a dry mass of about 30 tons and it wants to land 25 tons in the surface, and the crew ferry has a 5-ton crew capsule. So that's obviously way more than we can land. Here is the heat shield for the Curiosity rover. Here's the man's head right there. This is a 15-foot diameter heat shield for a 1-ton lander. For a 70-ton lander, we'd require an expendable heat shield 126 feet in diameter. It's not realistic for a Mars reentry. It is realistic to do an aero capture, but I don't think it's realistic for a reentry. And you'd have to throw the heat shield away. You wouldn't be able to reuse it again. Here it comes in. And this goes through the whole argument about how the thing gets down to the surface. So supersonic retropropulsion is the way you do it. You get down to between Mach 5 and Mach 3. The Mars ferry, all of them, have rocket engines which are sealed inside the engine compartment, and their edges of their nozzles are flush with the heat shield, plus the vehicles are canted out about 20 degrees to prevent the rocket exhaust from being pushed back against the bottom of the vehicle. You need about 8. Now this just appeared in the Aviation Week about 3 days ago. So the concept of supersonic retropropulsion is now getting serious attention. The people at Georgia Tech have been doing work on it for a number of years. And in fact, the whole problem of entry, descent, and landing on Mars was really first discovered by the Georgia Tech people back around 2004. So we've now known about the problem for 9 years, and we've already have a solution for it. We do need testing. These vehicles need to be tested using suborbital trajectory. So this is a chart. This line shows the current option right here, rocket power for the final descent. And then during the first phase of entry, what I call passive drag, it uses the heat shield. And so all the rest of it, down from below Mach 6 down to below, Mach 2.2 or whatever, is rocket power all the way down to the surface. It all depends on how you can save mass, but also you cannot build another aeroshell, a hypercone, decelerator, whatever on Mars. We don't have a factory on Mars to build those, but you can produce propellant on Mars. So this is my little slide about flags and footprints. Anybody seen Russian nested dolls? The Russian nested doll is called a matryoshka. To me, that's a metaphor for an object with another similar object inside it. We don't want to do this. This is a no-no. because that means you take the outer object and you throw it away. And you take the next object and you throw it away, just like Apollo. And you end up with a little tiny capsule, which you never use again. So this is a bad idea. So this goes off to the case for reusable Mars ferries. Provides additional backup vehicles. You wouldn't have to keep sending a new ferry to Mars for every 25-ton payload you wanted to land, and you wouldn't have to send additional propellant from Earth for every payload you wanted to land. Once you have your fuel plant on the surface, the fuel comes from Mars. So this talks about the design of the ferry. I'll go through this a little bit faster here to get to the... what this is really is a single stage to orbit and back vehicle for Mars. It takes about 1/4 of the energy on Mars to get to orbit that it does for Earth. So a cargo ferry down here would carry about 25 tons of modules and equipment down to the surface, 20 tons of propellant back to orbit, 15 tons of which you use for descent, and 5 tons you put back in your depot. The crew ferry, with its 5-ton crew cabin, would carry a crew with 20 tons of cargo and a crew and 15 tons of propellant back to orbit whenever you wanted to go back. So this makes it easy to go up and down from orbit. So the crew and cargo designs have about 70 tons of mass at descent and 125 tons at liftoff, with 20 tons total ascent payload and 25 tons for descent payload. Both vehicles have a base heat shield diameter of 14 meters, which is almost 50 feet in diameter, or 48 feet, something like that. Both ferry versions have a cargo bay to hold up to 25 tons of cargo, with a cargo bay door that open on the side below the fuel tanks. So the cargo is carried as close to the surface as possible. Both ferry versions have oversized fuel tanks that can hold 95 tons of propellant to go up, which includes 75 tons to go up and 15 or 20 tons for the subsequent descent. So it uses its own payload fuel to go back down again. This goes over some of the same material here. The total ascent and descent masses are the same for both ferry types. And this is a little table where you can see the descent, the mass is 25 tons, the structure is 30 tons, the fuel is 15. And you can see the percentage of it there. Then the more critical one, that the structure is 24% of the vehicle at liftoff. And that's the actual weight, 20 tons of payload to go up, 30 tons of structure, which is the same, and 75 tons of propellant to actually go up, which adds up to 95 tons of propellant in your tanks. So once you have the fuel production system in place on the surface of Mars, using Mars ice to make propellant, 100% of your descent propellant is brought up as payload made from local materials, Mars ice. So this is the Red Dragon scenario that Musk put out a couple of years ago, which gives you sort of an idea what a vehicle like this, where the rocket engine's aimed out to the side instead of straight down, would look like when it's landing. It's a pretty good painting. Now there is my actual vehicle. So here are the rocket engines flush with the heat shield, real close to the edge of the heat shield. The landing legs only pop out at the very last minute so they don't get damaged. These are the covered up thrusters for use in space, the arms thrusters. Here's more up here. This is a crew ferry. These are cargo ferries with no capsule in them. The robot basically grabs a link at the end of this cargo container, which is inside the bay with latches that hold it from moving around. You don't want a loose cannon on a Mars ferry any more than you want it on a ship. It pulls it out onto this flatbed truck, which then lowers it down. Very, very simple system. Notice that this is laid out in a line. These ferries would actually be at least half a kilometer apart. You don't want to land on top of another thing, of another ferry. Your crew base would be at least 1 kilometer away. If you have an accident, you don't want debris landing on top of your crew quarters. These paintings would show the rocket landing right next to the crew. No way. And then off in the distance, we have the fuel production plant. That would be also about at least one half to 1 kilometer away from the landing site. So this gives you an idea what this looks like. The lighter part of the stuff is at the top, the hydrogen. Then the heavy stuff is at the bottom, the liquid oxygen in your container, your cargo container, or it could be a truck, it could be a pressurized rover, it could be a habitat, anything that fits into a 4.5 by 4.5 by 8 meter long space. You can see the canted nozzles that go out to the side and the landing legs. Here's the arrangement of the rockets with the AMS engine in the middle. And here's a slice taken through the cargo bay deck, showing the 4 liquid oxygen tanks with the arrangement of the cargo bay in the middle of the cargo container. Now that's the same thing, but we've added a crew capsule. See the gray thing on the top? So that one can only carry 20 tons down instead of 25. Otherwise it's identical. And that's a chart that shows the distribution of mass. Note that the pie